Welcome students. The session is for CBSE Class 12 Physics in chapter Wave Optics. In the previous sessions you studied about ray optics. This is the next chapter, Wave Optics, of the same unit, presented by Ms. Geeta Manikandan. Okay, let's start off. Theories of light. There are many theories of light, like for example the corpuscular theory, wave theory, electromagnetic theory, Planck's quantum theory. Why is it we have so many theories? Is one theory not good enough to explain it? Yes, one theory is not good enough. The thing was, when a theory is proposed, it should be able to explain all the phenomena that is observed. Like for example, here light we're talking about. A theory is proposed. That theory should be able to explain all the phenomenon or all the behavior of the light. Corpuscular theory was proposed by Sir Isaac Newton in 1675, that is the 17th century. According to this theory, the light is actually made up of tiny particles, and he called it as corpuscles. Okay. So with this theory, he was able to explain reflection, refraction and rectilinear propagation of light. But these are just not the phenomenon observed. There are many others like interference, diffraction, polarization. But with this theory, all those phenomena could not be explained as to why they're behaving like that. That is why they had to come up with another theory. That was by Christian Huygens in 1678. See, just 3 years after the first theory, he proposed the wave theory of light. He said, no, light is not made up of tiny particles. It must be a wave. That's why it's behaving like that. And with that, he could actually explain reflection, refraction, interference, diffraction. But the problem was, he assumed light to be a longitudinal wave. That means it's a wave which can travel or propagate through a medium. That's when Fresnel and Young stepped in and he said, no, the light is actually not a longitudinal wave, it's a transverse wave. And they could further give explanation to the polarization of light. But then again, light is a transverse wave, but if you understand the actual definition of a transverse wave, you know that even a transverse wave needs a medium to propagate. And how come light is able to travel through vacuum? That is why Maxwell, he came up with the electromagnetic nature of light. Okay. So what he said was, no, light is actually made up of electric and magnetic fields together. It's not just a wave which is a transverse or a longitudinal wave. It is made up of electric and magnetic fields, and that is why it is able to travel through vacuum. Okay. After that, see, and this was proposed by Maxwell in 1873 that is in the 19th century. It's almost been a century before a proper or acceptable theory was proposed, right? See, Christian Huygens proposed it in the 17th century. Maxwell's theory is in the 19th century. Okay, so it's almost been a century between these two. And later, Planck came up with this idea, saying that, see, some phenomena can be explained based on the particle nature of light, whereas some can be explained based on the wave theory of light. He proposed a quantum theory. He said maybe light is actually made up of small packets of energy called photons. Okay, so this is called as Planck's quantum theory of light. Einstein accepted this, and in 1905 he actually used that theory to explain the concept of photoelectric effect of light. Also based on this theory, they could explain all the other phenomena like reflection, refraction, interference, diffraction, polarization. Then de Broglie came up with this idea that maybe light is dual in nature. That means light is made of both particle nature and wave nature. So wherever needed, you can consider the particle nature, and wherever needed, we can consider the wave nature to explain a phenomenon. So now you know why we have so many theories, because when one is not able to explain the theories, that is when they come up with another theory and so on. So every theory is like an upgraded version of the previous one, isn't it? Yes. Okay. So which theory are we going to study here? We're going to study the wave theory. Proposed by whom? By Huygens in detail. We're going to study about this. So this is Christian Huygens. See, he lived in the 17th century. I think he proposed the theory in 1675. That is about 20 years before his death. Okay, getting into the chapter, ray of light. What's a ray of light? An arrow drawn perpendicular to a wavefront in the direction of propagation of a wave is called a ray. So in all your previous classes, you would have studied that this is how you draw a ray of light, an arrow going in straight and line, and it is incident on some reflecting surface, gets reflected. Again, you show it by an arrow to show the direction. Then you draw the normal. You can draw the angle of incidence, angle of reflection, and so on. Okay, now in this definition, if you see there's a new word which says wavefront. What is a wavefront? Why is the ray perpendicular to the wavefront? Let's see what's a wavefront. Now wavefront is defined as the continuous locus of all such particles of the medium which are vibrating in the same phase at any instant. This diagram right now shows you what is a wavefront. Okay, does it look like I'm speaking some alien language to you? Did not understand anything about the definition, right? Okay, let me explain wavefront to you in English. Okay, look at the video. You can see that the soldiers are marching. How are they marching? They're all marching in a straight line. Okay, the direction is perpendicular to that straight line, isn't it? Yes. So each line of this whole parade can be considered as a wavefront. Right now, the first row is the front row, right? So that is called as the wavefront. If we consider this whole battalion as a wave beam moving, okay, the first row is the wavefront. Suppose you missed out the first row, you can always consider the fourth or the fifth row as your wavefront, because that is when you started observing it. Because they're all parallel to each other, you can consider any one of them from the time you're starting to observe that as the wavefront. Okay, so here if you see a ray of light, say a beam of light is incident on the surface. These are two rays. Let's say I have to draw the wave direction. Okay, this line shows the wavefront. How is it drawn? It is drawn perpendicular to the direction of the ray, isn't it? So this is how the wavefront propagates. As it is moving, it goes and gets incident on the surface. Okay, after it is incident, what does it do? Based on the surface, it can get reflected or refracted. Let's consider this to be a reflecting surface, and so the rays will get reflected. Okay, so this is the reflected ray right now. So how should I draw my wavefront? I should draw them perpendicular. Okay, so if there is a ray which is traveling here, okay, it will get reflected this way, right? So all these rays have a wavefront which is perpendicular to them. So this shows the propagation of the wavefront. It goes about like this. Okay, so now you understood what wavefront actually means. It is the continuous locus. Okay, all the particles in a particular row of the medium which are vibrating in the same phase at any given instant of time. So if any row I choose in this particular parade, they're all going in the same phase, right? So that is what a wavefront means. Hope you've understood this. Next, now that you've understood what is a wavefront, it's a new term that you've learned today. Let's see what are the different types of wavefronts. Okay, a plane wavefront. What you saw in that picture is a plane wavefront where they're all just plane surfaces marching one behind the other. The video that you see is actually a series of plane wavefronts moving along the x-axis. Okay, next, spherical wavefront. Okay, suppose the light is originating from a point source. Right now all the plane waves are incident on a, say, on a wall, and there's a tiny hole in it. So the light has to come out through that hole. Okay, so now the hole is behaving as a source of light. So when it is coming out through a point source, you're saying that the waves are not straight anymore, they're curved. Okay, they're all curved and they're coming out in a spherical manner. This video shows how the spherical wave fronts move. Okay, so this video shows the top view of a spherical wavefront. See all the plane wavefronts. Once it comes and hits the wall, it is coming out through that small hole in a spherical way. So the plane wavefront is right now, it's not a straight line, it's a curved line, it's a spherical wavefront. Okay, in 3 dimension, this is how it looks. Next, cylindrical wavefront. Now, when the source of light is not a point source, it's a slit. You see that? It's a slit here. Okay. So, if it's a slit of light, it's a linear shape. So, what happens? The light that is coming out is curved, but then it is not completely spherical. It is cylindrical in nature. So, when your point source or your source is a slit, is a linear source, what happens? The waves that are coming out of it becomes cylindrical in nature. So it is cylindrical, it's not spherical. You can see the difference between the two. Okay, now coming back to the first one, the plane wavefront. How do you think a plane wavefront originates? You saw that the spherical wavefront originates through a point source and a cylindrical wavefront originates through a linear source, right? Now how do you produce a plane wavefront then? It's nothing but as the spherical or cylindrical wavefront advances, its curvature starts decreasing progressively. Okay, so what it means is, suppose you have a point source, say a bulb. Initially, when you look at the wavefront, they're all spherical because it's a point source. But as you go farther and farther away from the source, you'll see that the radius of curvature is becoming too large. It's so large that you can as well consider it as a plane wavefront instead of a curved wavefront. So that is what a plane wavefront means. So now you have studied about the 3 different types of wavefronts. That is the spherical wavefront, cylindrical wavefront and plane wavefront. Next, coming to Huygens Principle. Okay, according to Huygens Principle, each point on a wave is a source of secondary waves, which added to give a wavefront at any later time. Totally sounds like Greek and Latin, right? Did not understand a word of what I just now read. Yes? Okay. Now let me explain Huygens Principle to you in English. Okay? In simple terms. Let's take the example of the situation right now. Okay? We are in a pandemic, right? Corona is spreading everywhere. Okay, let's take this guy as an example. Now, how does corona spread? Okay, let's say one person is infected with corona. Okay, he is a source. He can infect all the people around him, right? He can infect the people around him. Once he has infected them, they start behaving as a new source, right? So, this person becomes a new source and he can infect people around him like he is a new source, correct? Okay, the same thing can happen to all the other people also which the first person infected, right? Yes. Okay, it's similar to that. Okay, let's say a wave is originated from a point source here P. This is the wavefront. Okay, the wavefront is here and every point on it starts behaving as a new source. Now this video clip shows you that initially the wave is originating from this point. Okay, as it is moving ahead, you will see that every point on that secondary wave, okay, it's behaving as a new source and creating the secondary waves. Okay, never thought the corona pandemic would be helpful in explaining Huygens principle. Okay, it's very similar to that. Hope you have understood what Huygens principle actually means. It means that a wavefront can actually, when it is expanding, every point on that wave can actually act as a secondary wave and so on. Cool, isn't it? Okay. The principle is based on actually the following assumptions. Okay. Each point on the wavefront acts as a fresh source of new disturbance, and it's called as the secondary wavelets. Just like I told you, the initial person, he can infect the other people, and every one of them can act as a new source. Similarly, each point on a wavefront can act as a fresh source, okay, of new disturbance, and these are called as the secondary waves or wavelets. Okay. Also, the secondary waves spread out in all the directions with the speed of light in the given medium. That means if the one person is affected, he is affecting the other person, he can affect everybody around him, right? In all directions. The secondary wavelets spread out in all directions with the speed of light in the given medium. Okay, like this. See, it can spread out in all directions. Now, the next point is that the new wavefront at a later time in the given forward envelope or the tangential surface of in the forward direction of the secondary wavelet at that given time. Okay, what it means is it is only given by after a certain time interval. What happens? The wave only travels in the forward direction. It does not go back to the source. See, this orange circle is actually approaching the center, right? So after a certain interval of time, you will see that the ripples are only going outwards. Okay, they keep going outside. They don't tend to come towards the opposite side. They don't tend to come backwards. It's like the pandemic itself. Suppose the first person has got immunity, the spread only goes farther and farther away. It doesn't tend to come back to the people who already have got the virus. Maybe they have become immune to it, isn't it? I don't know how somehow corona perfectly fits this scenario. I'm explaining Huygens principle. Okay. Now, let's see how we can explain the different light phenomena that we observe. Okay, so based on Huygens wave theory. So the first phenomenon that we observe, very normal one, is reflection. So reflection on the basis of Huygens wave theory. Okay, you see this is a surface and the light is incident on it and the wave fronts are moving ahead. Okay, let's not see the red part of it. We are only looking at the blue wave fronts, which are the reflected light. Okay, how do you explain this based on the Huygens wave theory? It's not just you should be able to explain it, you should be able to prove it. Now we have to prove the law of reflection using the Huygens principle. Okay, so this is what is the diagram. Using this diagram, you will be actually able to prove it. You have to prove what the law of reflection, which says that angle of incidence is equal to angle of reflection. Okay, panicky? All seems Greek and Latin and too complicated, is it? Okay, no need to panic. Okay, I will explain this to you again in English. Okay, here comes the proof in English. Okay, let's go at a comfortable pace. Let's say this is a reflecting surface you see right now on the screen. Let me call this as X and Y. Okay, X and Y. Now let's say a beam of light is incident on the surface. Okay, let's say it is traveling in this direction. Okay, it is incident on the every time you're drawing a ray diagram, you have to draw the directions. Don't forget that. So we have a ray here. It's a beam. Okay, two rays are incident on the reflecting surface. Okay. Now, let's say this is the wavefront. You've already studied, right? So let me draw the wavefront along the perpendicular direction to the direction in which it is traveling. So this is perfectly 90 degrees that I have considered. Okay. So if you notice that these two are traveling this particular wavefront, they're all parallel to each other. So by the time this ray has reached here, this ray also would have reached this point, correct? Yes. What happens to this ray when this ray is here? This ray has, let's call this as ray A and it is incident at point B. Let's call this as C and it is incident at D. Okay. When the ray AB is incident at B, C is still traveling, right? What will B do? Okay, let's draw this normal line. It will get reflected, correct? Yes. But by the time B travels to this point, this ray would have just reached D, isn't it? Okay. So this is the reflected ray. This blue line shows the line which is the wavefront of the reflected ray. It is again drawn perpendicular to it. Okay. Now the time taken for the, let's say, ray to this ray to reach here is the same time this ray takes to reach this particular point. Okay, so did you understand that the ray traveled this distance, and in the same time this ray has got reflected along this particular line. So let's say t is the time taken by the light to get reflected to this point. Let me call this as let's say E. Let me call this as E, and let's call this as F. Okay, so the time taken for the ray to reach from B to F is the same as the time taken for the ray to travel from E to D, isn't it? So let's say they're traveling with some velocity V, which is nothing but the speed of light. So let me call this as C. Okay, so CT will give me the distance traveled, correct? Distance traveled by the light. Okay, let me write it. So CT will give me the distance traveled by the ray, okay, from B to F and also E to D. Okay, so do you agree that the distance BF is equal to the distance ED, isn't it? Okay, now let's take this triangle. Okay, before that, which is the angle of incidence? Let's say this is the angle of incidence, isn't it? This ray is incident on the surface. This line is the normal line. Okay, so this is the angle of incidence. Where is the angle of reflection? Okay, let's say this is the reflected light. This angle measured from the normal will give me the angle of reflection. So what do I have to prove? I have to prove that angle of incidence is equal to angle of reflection using Huygens principle. Now let's take this triangle BED, okay, and triangle BF and D. Okay, in these two triangles, if you notice, we have the common side. BD is equal to BD. Correct? This side is a common side here. Next, if you notice, this is perpendicular. So this is also 90 degrees and this is also 90 degrees because it's the wavefront that we have drawn. Therefore, we have angle E is equal to angle F. Okay. Also, we notice that BF is equal to ED. Okay, so in this triangle we have proved that two sides are equal and one angle is equal. So in your maths you would have studied that by the rule of SAS. Okay, by that rule you can say that these two triangles are actually congruent to each other. Okay, they are or similar to each other. Okay, so if they are similar to each other, now inside this triangle, do you agree that this is angle I? This is 90 minus I, okay? This is 90 minus R. So obviously this has to be R and this has to be I, okay? So in the triangle, we can say that angle I is equal to angle R. Hence, your proving that you can, uh, using Huygens principle, you can actually prove the law of reflection, that the angle of incidence is equal to the angle of reflection. Okay, hope you've understood this. If not, you can go back and listen to us again. Okay, let's move ahead. Refraction on the basis of Huygens wave theory. Now we've studied about reflection. Now we have to see about refraction, because that is another phenomenon we observe using light. Correct? So here if you see, you can see that the wavefront is traveling towards the surface. These are the wavefronts. These two lines are the wavefronts. Once they're incident, this medium happens to be a transparent medium, and so the wavefronts are entering, and this is what is happening. Now you have to prove the law of refraction. What is the law of refraction? We have to prove that the Snell's law, which says that sine of I divided by sine of R is a constant. Okay, we shall be using this diagram. Okay, again, you don't have to panic. We'll do this at a slow pace in English. Okay, let's say this is a transparent medium. Okay, let me draw the normal, and let's say a rays are incident along this direction. Now this is the direction along which it is incident. Okay, now it is going this way. Now the first ray has already reached the surface. The second ray is still there. Okay, I will draw the wavefront. This is the wavefront. They're all traveling parallel to each other, right? They're all traveling this way. Yeah, they're going in this direction. Okay, so this is the wavefront. When this part of the beam has traveled and reached here, this is still here. Okay, this ray is still here. So what happens? By the time this ray reaches this point, okay, this ray has already traveled into the medium and traveled a distance of this much. Okay, let's draw the wavefront there. So this is the wavefront of the refracted ray. Okay, so let's name this. Let's say this is A and this is B. This is C. Let's call this as D. Let this be D. Let this be F or E. Okay. Let this be E. Okay, let's leave this also as F. Okay. So what is happening? The time taken for the light to travel from B to C is the same as the time taken by the light to travel F to E. F to E is a longer line and BC is a shorter line, you observe. Why is that so? Because this now is a rarer medium. Okay, let's say this is mu1 of refractive index mu1. Let's say this is a denser medium. Okay, this is a denser medium. Let's say its refractive index is mu2. Okay, this ray right now is still traveling in the rarer medium, and so it is able to travel at the same speed. Let's say it is traveling with a distance v and it is taking a time t. Let's say this is v1 and it is doing so in the given time t. In the same time t, this ray has already entered into the denser medium, and this happens to be traveling with another speed v2 in the same speed. Okay, so the distance traveled is v1t, and the distance traveled inside the denser medium is nothing but b to c. It is v2t. Okay, the velocity of light changes in a denser medium, isn't it? So that's why I have two different velocities here, v1 and v2. Okay, now what do I have to prove? I have to prove that sine I by sine R is equal to a constant. Okay, which is the refractive index. Now let's see, where is the angle of incidence? This is the angle of incidence. Okay, this is the angle of incidence, and this happens to be the angle of refraction. Correct? Okay. If this is I, this also happens to be I. Right? We saw during the reflection time that if this is I, this should be actually 90 minus I. And so this will also be I. Okay. Now if this is R, this angle happens to be R. This is 90 minus R. This is 90 degrees. So this has to be R, right? In this triangle. Now to prove this, let's consider this triangle. So right now we're considering this triangle BFE. Okay. So in this triangle, what is sine I? Sine I is equal to opposite by hypotenuse. So the opposite side to I happens to be this side. Okay. So I can write it as FE divided by the hypotenuse. This is 90 degrees. So the side opposite to 90 degrees is the hypotenuse. So it is BE, right? Okay. Here I have defined this distance as V1. And BE is nothing but, let's keep it as BE itself. Okay. Now let's see the next triangle, which is the low triangle, triangle BCE. Okay, it is this triangle. Here sine R is equal to, inside the triangle, if you see R is here, we're taking sine, so opposite side is nothing but BC divided by the hypotenuse. Hypotenuse is nothing but BE again. Okay, because this is 90 degrees. So again I have defined BC as V2 divided by BE, isn't it? Now taking these two together, if I do sine I divided by sine R, what will this be? It will be V1t divided by V2t. BE and BE will get cancelled. Here T and T can get cancelled. This is nothing but V1 by V2, which is nothing but the speed of light in the first medium divided by speed of light in the second medium. You can define it as V2 by V1. You've studied this definition, isn't it? The refractive index of the second medium with respect to the first medium can be equated to the velocity of light in the first medium to the second medium. So we have proved Snell's law, sine I by sine R is equal to a constant. We have proved the law of refraction using Huygens principle. Hope you have understood this. Okay, I really went at a slow pace. If you haven't understood, you can go through it again. Okay, you can listen to it again. Next, there's a fun fact, let's see. Okay, you know how long does the light take to travel from the earth to the moon? Actually, it takes around 1.3 seconds. Light takes 1.3 seconds to travel from the moon to the earth. And here we are talking about two light rays which are very near to each other. Okay. And we are talking about the small time t which it takes to travel this small distance. Okay. Which cannot be even seen, isn't it? Yeah. Anyways, let's not bother about it. The point is we have proved the reflection law and refraction law using Huygens principle. So let's not talk about these facts. Now let's recapitulate. Okay, we have studied in this session about a ray. Okay, what's a ray? It's a arrow perpendicular to the wavefront, isn't it? It's a direction, it shows the direction of propagation of the wave. It is perpendicular to the wavefront. And you know what is a wavefront? It's the all the particles which are vibrating in the same phase at any given instant of time. We have studied all the types of wavefront. Yes, that is the cylindrical, the spherical, and the plane wavefront. We have studied the Huygens principle of secondary wavelets. We used the uh, current scenario, the pandemic, corona, and I explained how the Huygens principle works, and we have understood what are secondary wavelets. And based on wave theory, we have seen how reflection works, and we've also proved the law of reflection, which is the angle of incidence is equal to angle of refraction. We have proved that, and we've studied about refraction based on Huygens wave theory, and we also proved Snell's law based on wave theory, isn't it? Okay, so we've come to the end of this session. In the next session, we will be studying about the principle of superposition of waves, interference of light, Young's double slit experiment, which actually proves interference, and then coherent lights and incoherent sources, and so on. Okay, good. That I really enjoyed doing this session. I hope you too enjoyed listening to this. Yes. Okay, students. Also, there is French word. So we've come to the end of the session. Thank you. So meet you in the next session.